Today I'm truly honored to introduce Dame Jocelyn Bell, who is a distinguished speaker who has flown all the way from the UK to visit us today and tomorrow. Dr. Bell is currently visiting professor of physics in Oxford University. She's been a dean of science and was for 10 years the dean of Open University. And during this time, during her appointment actually to the Open University, she doubled the number of female full professors of physics in the UK. She spent a year as a distinguished visiting professor at Princeton and was president of the Royal Astronomical Society from 2002 to 2004. She received her physics degree in Glasgow University, Scotland, and then a PhD in Cambridge in radio astronomy. During her time there, she discovered pulsars, opening up a completely new branch of astrophysics, work which was recognized by the award of a Nobel Prize to her supervisor, Anthony Hewish, in 1974. Sir Fred Hoyle made a remark later to a reporter, yes, Jocelyn Bell was the actual discoverer, not Hewish, who was her supervisor. So she should have been included. Jocelyn branched out subsequently in doing multi-wavelength astronomy. She has worked on telescopes, flown on high-altitude balloons, launched on rockets, and carried on satellites and built a radio telescope. Professor Bell has won numerous awards, to name a few: the Oppenheimer Prize, the Michelson Award, and the Magellanic Premium. Several universities from the US and UK have conferred honorary doctorates on her. She is currently a fellow of the Royal Society and was elected as Foreign Associate of the US National Academy of Sciences. In her spare time, during this busy schedule that she has co-edited an anthology of poetry with an astronomical theme, Dark Matter, Poems of Space. Today, she's going to talk about the discovery of pulsars and their extreme physics. So let's have a round of applause for Professor Bell.
Thank you very much. Thank you for the opportunity to be here and for the welcome. I'm very grateful that I'm having this chance to visit Northwestern and talk with faculty members and postdocs and so on here. It's a great opportunity for me, so very many thanks. So I'm going to talk about two things mainly under this heading, but there'll be a bit more context. I will talk about the discovery of pulsars, and if I'm not careful, that takes about an hour and a half. I'll say a little bit about the stellar context of pulsars, a bit about some pulsar properties, but in particular, I don't know if any of the solid-state physicists have come, but I thought I would say a bit about the inside of one of these stars, where there is some very condensed matter physics. Really bizarre, very condensed matter physics. But I am going to start with the discovery of pulsars, because that's what Farad particularly asked me to talk about. And it's 50 years ago this year. Hard to believe, but true. And so 1967. 2 years previous to that, I had turned up at the University of Cambridge to start studying for my doctorate, my PhD. And at that time, when radio astronomy students appeared in Cambridge, they got given a set of tools. And I still have my tools. These are they. And they're not dinky microelectronics tools, they're the real thing. Because we were going to be doing a lot of working with wire, cables, sledgehammers also focused, but they don't photograph so well. And I didn't get given my own, though I probably should have. I have to say that there were one or two curious people called theoreticians who didn't get given a set of tools. but the rest of us did. And I spent much of the first 2 years as a group of about 6 people building a radio telescope. And this photograph is taken near the end of the process. It's a very big radio telescope. It would occupy the space of 57 tennis courts. It was for a relatively small grant of money from the Funding Council, although we don't advertise this too widely in case it undermines anybody else's projects. But that sum of money at that time would have bought starter homes for 3 newly married couples, to give you an idea of the kind of sums we're talking about. And it took half a dozen of us 2 years to build it. And what is happening here is working in the field, and nearly all the work was literally in the field. I tried to convince people that this is typical working conditions for a PhD student. This is my technical assistant, Don, and this is me. And there's a little hut, and there's another little hut away down there. And we have some very special low-loss cable, airspace cable, that you could not coil up and take indoors. So we cut it to the right length, which equals the spacing between these 2 huts. And I worked inside these huts, putting the plugs and sockets on the ends of those cables. And we're now testing them. We're measuring the impedance of the cables, and there is a slotted waveguide here. And what you don't see is about 400 yards of cable back to the nearest power outlet. You know, literally working in the field. The finished product looks like this, and it looks homemade because it is homemade. It's actually fairly typical of long wavelength radio astronomy antennae. It's a field that's coming back into fashion, and if you look at things like LOFAR and MWA, they're quite like that in many respects. A lot of posts and wire. The posts, there's over 1,000 posts, are basically to keep all this out of the wet grass, because wet grass is an electrical short. And if you lay your antennae on the wet grass, you get no signal because it's run to earth. So although the posts are the most visible thing, they're only there to keep it out of the grass. These slanting posts carry a reflecting screen made of strands of wire. Because it's long wavelength, you don't need solid mirrors. Strands of wire will do the job. And here is one antenna and its feeder cable curling down to another feeder cable, which subsequently goes into normal coaxial cable and back to the laboratory. So there were 2,048 antennae with a wavelength of 3.7 meters or 12 feet, which is big. We actually used half wavelength antennae. There's a total of 120 miles of wire and cable in this antenna, and I was responsible for a good deal of it. Physically it was built as one continuous structure, but electrically it was in 2 halves. And I need my hands to demonstrate a moment. I'm not sure about the high school's kids, but others of you will know about young slits, 2 slits and interference. You remember what happens if the slits are wide? The central, the lines cease to be sharp and become wider. And then if you put these 2 together, you end up with one large intensity fringe in the middle and a couple of weak ones either side. And that's what we were using, an interferometer with the 2 halves abutting. I had used transistors as an undergraduate, but when I turned up in Cambridge, they said, transistors? Yuck. Noisy, unreliable, we use valves. And they did for a bit more, but they've changed subsequently. So the project was to find quasars and also, less successfully, to try and measure their angular diameter. Because it was only a few years previously that Martin Schmidt had recognized that the first recognised quasar 3C48 was actually an extremely distant object, which raised all sorts of questions because these were some of the most powerful objects in the radio sky. The optical astronomers said there's a funny star-like thing there. And if you put them at enormous distances, there are questions about how do they generate such an intense radio signal. So they were the sexy object in the mid-1960s. And this particular project was to find more of them, because there were only 10 or 20 known at that stage. And this project did find more of them. I found about 100 more quasars through this piece of research. There are many, many more today. Some of you may have been told that you can distinguish between stars and planets in the night sky because the stars twinkle and the planets don't. Sort of true. Rough guide. The stars twinkle because they've smaller angular diameter. They're intrinsically bigger, but they're much further away than the planets, so they've got a much smaller angle that they subtend, whereas the planets subtend a bigger one. And these narrower stellar images suffer scintillation as the light comes through the Earth's atmosphere and the star twinkles. Similarly, in the radio galaxies are a bit like the planets. They have large angular diameters. The quasars have very small angular diameters. And the quasars scintillate or twinkle. In this case, not because of the Earth's atmosphere, but because of the solar wind in the space between the planets. It's not entirely uniform. There are clouds of enhanced electron density in it. I don't know if undergraduates these days do a diffraction experiment with lycopodium powders. We certainly did as undergraduates, and it's the radio analogy of that, with the screen moving past you because the solar wind is blowing out from the sun. So the quasars will twinkle, scintillate, and the radio galaxies won't. So this is a very, very neat technique for spotting quasars. But it does require that you use a short time constant, a short integration time or exposure time. If it's too long, you blur out this scintillation. So we were using a time constant of 1/10 of a second, which was really very short compared with what people used at that time. And it was pretty boring. Used the radio telescope to map that declination strip for one day. Next day that one, next day that one, next day that one. Actually, we had 4 beams, so we did 4 strips at a time. And then on day 5, day 6, day 7, day 8, day 9, day 10, you know the pattern. A lot of research is quite boring, isn't it? And I did that for about 6 months, and that's what identified another 100 quasars. At that time, the University of Cambridge had 1 computer. It would occupy a room of about this size, and it had less memory than your laptop. And very few academics, very few faculty members had access to it. The ones that didn't had grad students instead. And my thesis advisor did not have access, so there was a grad student. And after spending 2 years building this radio telescope, the other 4 or 5 people moved on to other projects, and I was left to run it, to operate it, to do day 1, day 2, day 3, day 4. But because there was no access to a computer, the data came out on long rolls of chart paper. And they were long. The telescope produced almost 100 feet of paper every day. So 1 complete sky scan, 4 days, was 400 feet. And I ran it for 6 months, so I ended up with more than 3 miles of chart paper. And I can assure you I have looked at every 1/4 inch of that chart paper, some of it more than once. I very quickly got used to identifying the scintillating quasars. I also got used to identifying artificial interference. In those days, it could be badly suppressed cars or something that sparked, a sparking thermostat, a sparking high-tension power supply. Somebody allocated to the local police our radio frequency. They're protected, so we got them unallocated quite quickly. But all sorts of things could very easily cause interference, which with this huge collecting area was very visible. And on many of my observing charts, maybe 10% of the time was blocked by interference. What we're seeing here is the trace that I used the most. And we have, people further back won't be able to see much of this, but we have a signal that I couldn't make sense of and some low-level interference, man-made interference. And they don't look the same. Those near the front can perhaps see, you can see chart between the spikes on the interference, whereas over here you can't. The interference spikes go up and down, whereas this funny signal, they mainly go up. When we make those kinds of comparisons, we're doing Fourier analysis. Saying that we can see chart between the spikes is a comment on the frequency of the signal, its low frequency. And we're also talking about the amplitudes, plus and negative, just plus there. Now, the first time I saw this signal, I logged it with a question mark and passed on. And I probably did that 2 or 3 times. But it was only there very intermittently, about once in every 5 or 10 times that we looked at that bit of sky, it was there. And I had lots of things to worry about, but I logged it. I don't know how it is for other physicists, but I certainly remember as an undergraduate, things that I understood, I knew I could answer exam questions on. But things that I didn't understand, you have to learn parrot fashion until you understand it. And those things really, really bugged me. And I think this thing bugged me because I didn't understand it. And although I didn't realize at the time, it was lodging in the back of my brain. And after I'd seen it a few times, my brain said, "You've seen this somewhere before, haven't you? You've seen this somewhere before from this bit of sky, haven't you?" And then it's easy, because rolls of paper for that strip of sky are stored in one shoebox, that strip of sky in another shoebox, and so on. So you go find the right shoebox and you spread out the charts. Now, you need a lot of floor space for this kind of science, but you spread out the charts, you line them up. Yeah, I logged that one. It's not there, it's not there, it's not there. It might be there. It's not there. There it is. Oh, I missed that one. No. I logged that one. And that's this one. And they all line up. They're in the same declination, to use an astronomy term, and they're at very much the same right ascension. So I discussed with my thesis advisor what we should do about this, and the problem is here, chart's running at about 1 inch every 5 minutes, and all this signal is jammed up into a 1/4 inch. We need an enlargement. And the way you get an enlargement with this is to run the paper faster underneath the pen. Easy. So we just switch the pen recorder to a higher speed. No. Because the chart recorder runs out of paper after 20 minutes. And guess who is going to have to live at the observatory, putting a new roll of paper in every 20 minutes, day and night. Not a good idea. Next best idea. Grad student goes out to the observatory at about this time, switches on the high-speed recorder, switches it off at about this time, and back to normal. And I did that absolutely faithfully for a month. And it had disappeared. And I was making these high-speed recordings of basically receiver noise. And my thesis advisor got very cross. It's a flare star, it's been and gone and done it, and you've missed it. Those who aren't yet grad students should know that grad students serve the same function as the cat. They are for kicking. Well, I kept going out to the observatory and kept recording receiver noise. And then one day, by now the star was transiting at lunchtime, there was a very interesting lecture in Cambridge on aging, and I remember it well because of the circumstances. And I decided, stuff this, I'm going to skip going out to the observatory, I'm going to go to that lecture. And I did, and it was very interesting. And next morning went out to the observatory. It had reappeared and I had missed it. So I didn't dare leave. I stayed on and kept my fingers crossed, but it had been away for a month. So how long was it going to be around? And I got this recording. Ignore that one for the moment. Down the bottom are man-made artificial time pips, 1 second time marks, which are very kindly broadcast within Britain, and we recorded them. And hint, hint, no, hint, hint, pulse, 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 no, pulse, 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 several missing, back on beat. And you can see that the spacing is a bit over a second. It's about 1 1/3 seconds. And as soon as the transit was finished, I got the paper off the chart, and guess what? Spread it on the floor. And went along with a ruler, and yep, they're 1 1/3 seconds apart. We didn't do much telephoning in those days, but I decided I'd telephone my thesis advisor. He was teaching in an undergraduate laboratory, and he was probably dealing with some twit of a Cambridge student who thought his diffraction grating had 3 lines per inch. And then his twit of a grad student phones up and says, "Hey, Tony, you know that funny signal? It's a string of pulses, 1 1/3 seconds apart." Ah, well, that settles it. It's man-made. I wasn't so sure, but I couldn't marshal the argument because I hadn't expected that. But the reason it's not man-made is I've been tracking this thing for 3 or 4 months now, and it's kept sidereal time. It's kept its position amongst the stars. So if it's Joe Doe driving home from work in a badly suppressed car, he's getting off work 4 minutes earlier each day. 28 minutes a week, and it's been going on for months and nobody noticed. No. Tony came out to the observatory the next day at the appropriate time and stood looking over my shoulder, and that was one of the most scary bits of my PhD. This thing has been absent for a month. It showed 2 days in a row. Is it going to show today? And it did, and it produced pulses with the same pulse period. So Tony took away all my recordings and checked that it was keeping sidereal time, and admitted that it couldn't be artificial interference. But there's a big question about what it is, what it could be. Next suspicion was Jocelyn's wired the radio telescope up wrong. So is it some fault I've got wires crossed in a dramatic way? So we asked a colleague who had another radio telescope and their own receiver on the same observatory site, could they see it? And initially they couldn't, which was really scary. But then we realized it was slightly differently aligned from my telescope, and they had miscalculated by 5 minutes when it would appear in their radio telescope. If the miscalculation had been 25 minutes, we'd have all packed up and gone home. But 5 minutes late, it showed in that radio telescope as well. So it's not a fault of this radio telescope and this receiver, but it is on the same site. And we were getting really puzzled. We could see it had to be small and it had to be big. It has to be small because it's giving short pulses. It has to be big because after a few days we can see the pulse period is really steady. it's not tiring, it's not slowing up. So it's big, it's got big reserves of energy. So it's small and it's big. Actually, in physics, you often have to frame the question, well, you always have to frame the question really precisely. It's small in the sense of diameter, but it's big in the sense of mass. That didn't make much more sense at the time. With hindsight, we can see what was going on, but at least we... Now, a little bit of physics teaching here, and I've forgotten to test this bit of the PowerPoint, so we'll see what happens. You probably all know about the dispersion of light, how if you shine light through a prism you can get the different colours. It's because the different wavelengths travel at different speeds through that glass prism. There is a radio equivalent, which was first discovered by amateur radio amateurs, radio hams. And it's what's called whistlers. And I'm not at all sure this will work, but if it doesn't, I can whistle. No, we've not got it properly wired up. What happens is there's a lightning stroke on the far side of the Earth. The lightning stroke generates a radio wave. And that radio wave, that pulse, contains in it a whole range of frequencies. The radio signal then travels round, following the magnetic field lines, to the other side of the Earth. And as it travels, the different frequencies travel at different speeds because of the ambient electrons. Electrons cause the medium to be refractive. The high frequencies arrive before the low frequencies. And what your radio amateur here in the US will hear from a lightning stroke on the far side of the Earth is which is called a whistler. And graphically it looks like this. The high frequencies arrive first, followed by lower and lower and lower frequencies. Now we used the same argument with the pulsar signal, assuming it's emitted by whatever it is, and then travels through interstellar space. It might well arrive here on Earth with this same kind of descending whistle. So John Pilkington, one of the postdocs who was working with us by then, set up 2 radio receivers tuned to slightly different frequencies and saw that it arrived first in the high frequency and later in the low frequency, which is what you expect. But because of the delay between those two, we could estimate how many free electrons the signal had come past and therefore get an estimate of the distance. And it turned out to be about 200 light years, which puts it beyond the solar system, but well within the Milky Way, our galaxy. So, we're still not doing very well for understanding what it is, and one not very loudly spoken possible model was, is it little green men signalling to us? They'd be, if it was little green men, they'd probably be on a planet going round their sun. And as their planet comes towards us, the Doppler shift piles the pulses up on each other, and as it moves away from us, the pulses get more spread out. So we started a project to, well, Jocelyn continued going to the observatory every day and switching on the high-speed recorder so as we could measure the pulsar period and look for any changes. And we found a change. We found a Doppler shift. Because the Earth is going round the Sun, and Doppler shift works for motion of the receiver as well as motion of the source. So we proved that the Earth went round the Sun, but otherwise weren't getting very far. And we tried everything we could think of. We're now about a month in from finding the first pulses, and I worried about a corrugated metal air hanger just to the south of the telescope. But actually, because the wavelength is 12 feet and the corrugations on a hanger are something like this, those waves don't see these corrugations. So that was out. I tried to calculate if there could be a satellite which was in an orbit that moved to look like the stars. The period, 4 minutes shorter each day. Couldn't find a stable orbit for such a satellite. We worried about all sorts of things. Tony even wrote to other astronomers who do keep sidereal time, saying, have you possibly had an experiment going since September, August that would cause interference? Ask a stupid question, you get a stupid answer. No, of course they hadn't. And keeping an eye on the time, I remember one evening going down to Tony's office to talk to him. Tony's office normally had the door open, but today the door was shut. So I knocked on the door and Tony said, come in. I put my head round the door and Tony said, come in, Jocelyn, and shut the door. So I went in and shut the door. And there was Tony, there was Martin Ryle, who was the head of the group, and there was one of the other senior radio astronomers. And they were having a discussion that I probably should have been in, even from the start. How do we publish this? We have one. We don't know what it is. We're pretty certain it's not interference, but we don't know what it is. How the heck do we publish this? We didn't resolve the issue. I went home for supper that night very cross. Why do some bloody little green men have to decide to use my frequency and my telescope to signal to Earth? But my logbook from the time is full of plaintive, I'm now 500 foot behind with the chart analysis. I'm now 1,000 foot behind. I'm now 2,000 foot behind. So I came back in to do some chart analysis that evening. And I had till 10 p.m. when the janitor locked the building. We didn't have keys, only the janitor. And you could be locked in or locked out, your choice. And it was coming up to 10 o'clock, and I was looking at a rather grotty bit of sky. Cassiopeia A is one of the strongest radio sources in the sky, and in Britain it is circumpolar. It does not set, but only just circumpolar. It grazes the northern horizon and then rises in the east and goes round and sets and grazes the northern horizon. And when it's due north, I could see it through the back of the telescope. It's so strong. And it was scintillating like mad. And there was probably about a foot or 10 inches of chart paper every day at sidereal time around about 11:30, where it was a washout because of flipping Cassiopeia A at lower culmination, causing rubbish. And I was looking at that bit of chart paper, and there was a tiny gap in all this rubbish. And there was a curious little, interesting. 2 minutes to 10. Get the shoebox, pull out all the charts of that bit of the sky, lay them out. Yep. Grot. Yep. Right. Pile the charts on the desk, run out of the laboratory as the janitor is turning the keys behind me. That bit of sky is transiting at 2 o'clock in the morning. And I've got to be there. And this is December the 21st. And I'll tell you why I remember the date in a moment. December the 21st, or maybe the 20th, going on to the 21st. It was very, very cold. And for reasons I never understood, when it was cold, something in one of the receivers misbehaved. And the whole thing was at half sensitivity. And I got out there at 2 o'clock in the morning and it was at half sensitivity. So you do all the traditional things. You thump the equipment, you breathe on it, you swear at it, you flick switches. And I got it to work at full strength for 5 minutes, and it was the right 5 minutes on the right beam setting, and in came pulse, 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 pulse. This time 1.25 seconds apart. The first was 1 1/3. And that for me was the really sweet moment. Because it's not little green men. There aren't two lots of little green men on opposite sides of the universe, both signalling to this inconspicuous Earth, using a crazy frequency of 81.5 megahertz, and a very, very stupid technique of amplitude modulation. It's something cosmic. Now, I had to go that night because the following day I was going with my boyfriend back to my family in Ireland to announce our engagement, to be married. And you can't have his engagement and her engagement. Both got to be there. So that duly happened. Tony kindly kept the survey running while I was away, which meant he put fresh paper in the chart recorders and ink in the inkwells, and piled the charts, unanalysed, on my desk. And when I came back 10 days later, Tony was in the meeting. I couldn't find him, but it was quite clear what I had to do. There was plenty of charts to analyse. And I sat down and started analysing it. Oh yeah, which one's that? Which? It's not? It's a third one? Gee. Okay, I'll finish this chart and then I'll come back and check up on this one. What? 2? 0833, 0950. We were subsequently both confirmed as pulsars. But at that moment, Tony appeared and I said, "Look, Tony. Oh, Happy New Year, Tony. Look at this. Look at this." "Oh, how many more have you missed?" "Go back through all your old recordings," which I duly did and didn't pick up any more. And these third and fourth were subsequently confirmed as well. And at that point, I stopped observing because I was within about 6 months of finishing. So I had to complete thousands of feet of chart analysis and write a thesis. Tony told me it was too late to change the title of the thesis. So there was a very black day when I realised I had to get this quasar business back up to thesis standard. From what I now know of university systems, I don't think he was right. But as a grad student, you believe your advisor. So we now understand these things to be rotating objects, probably very highly magnetized. These two cones represent the north and south magnetic fields, and out of this cone of magnetic field comes a radio beam, and when it shines on Earth we get a pulse. So we get a pulse once every revolution. Static version, pulsar, magnetic field line, radio beams coming out like this, rest of the magnetic field. The key point is that the magnetic axis is offset from the spin axis, so that the beam sweeps around the sky like a lighthouse. And that model is very broadly accepted. This magnetic field configuration, well, at a distance everything looks like dipole. Close up, dear only knows what it is. Could be much messier. So what is it that we found? These are stars. There's now lots of them known. What are they? So for the benefit of those who are not astronomers, stars are born, they live, they die. A lot longer than us, their lifetime, so they appear static, but they're not. And they're born in some of the dark parts of the galaxy, like the Horsehead Nebula and this dark lane. Anywhere where there's a good dark cloud, there's probably gas and dust. And if it pulls together, it'll form a star or a group of stars. Most stars, like the Sun, are shining because they're doing nuclear fusion reactions. Most are converting hydrogen to helium, some helium to carbon. Sun has been doing it for about 5 billion years and will do it for another 5 billion years. But not forever because it's using a fuel. Big stars like the Pleiades have more stages to their lives. These ones are 10, 20, 30 times the mass of our Sun. Because they're more massive, they've got a rather higher central temperature. There's more pressure. And the reaction rates are very temperature sensitive. One of them that's used and might well be going on in these stars, the reaction rate goes as temperature to the power 17. So you only need to put the temperature up a little bit and the reaction rate really goes. So these are shining very brightly because their reactions are going at great rates. And even though they're more massive than the sun, because they're burning so fast, they'll last a much shorter time. And they will go beyond converting helium to carbon. They'll convert carbon to other higher elements in the periodic table. There's a whole sequence of elements they can burn, all of which are endothermic, those fusion reactions, until they end up with iron or iron nickel in the core. And you cannot get energy out of iron. It's endothermic, not exothermic. Sorry, I think I said endothermic earlier. This is a photograph of part of the southern sky, part of the Large Magellanic Cloud. Lots of nice pink, red hydrogen gas. Many, many stars, glowing mass of stars and gas here. One star, inconspicuous star, picked out with an arrow. For the non-astronomers, the arrow's added afterwards. There aren't stars with arrows pointing at them to tell you where to look. This is the inconspicuous star. It has now exploded. It's what we call a supernova. It should have formed a pulsar. It doesn't seem to have done so. It may have formed a black hole subsequently or something. But pulsars, these stars, are the cores of these massive stars that explode. And about 95% of the star gets kicked out into space, and the core collapses down into something very small. The Crab Nebula, famous nebula, remains of a star that exploded about 1,000 years ago. A great puzzle as to how it kept shining. The emission from this nebula is what's called synchrotron emission, caused by energetic electrons, which should be getting tired and the nebula should be fading. It isn't, because there's a pulsar about there which keeps supplying fresh energy and keeps the nebula shining. So these objects have a mass a few times the mass of our Sun, something by 10 to the power 27 tons. We believe they have a radius of about 10 kilometres, and this is not a mistake. I do not mean 10 to the power something kilometres. If you put 10 to the 27 tons in a ball of radius 10 kilometres, it's very dense, comparable with the density of the nucleus of the atom. Consequently, there's strong surface gravity and strong tidal effects. So, if there were a mountain 1 micron high on a neutron star, the work you'd do climbing up that 1 micron against its gravity is comparable to the work you do climbing Everest against Earth's gravity. The atmosphere is also highly compressed. In the absence of electrical forces, the atmosphere is a couple of centimetres deep. With electrical forces, well, it might get to waist height. But, you know, if we lived on one of these stars, we'd be a different shape because we have to get our nostrils down there. Gravity bends light. So the strong gravity of these objects means you can see over the horizon, 20 or 30 degrees over the horizon. You can see 2/3 of the star just standing in the one spot and looking around. Gravity also redshifts light, so if there were little green men, they'd look like little red men to us. And they wouldn't be that shape. And gravity also affects clocks. So clocks on one of these stars would tick once every 2 seconds rather than once every second. There's also a very strong gradient of gravity. So suppose I'm going to land on one of these objects, and I'm coming in feet first because that's the ladylike way to land on one of these. And I'm being pulled down by the very strong gravity. But there's much stronger gravity on my feet than on my head. And it's sufficient to stretch the body. In fact, overstretch the body. So here's a stretched body. Technical term is spaghettification. But the spaghetti breaks into blobs and lands one at a time. A bit like tidal disruption around stars. Same theory. So visiting a pulsar can seriously damage your health. There's a huge magnetic field. We think it's about 10 to the 8 Tesla. To put that in context, your fridge magnet's about 100th of a Tesla, and a strong lab magnet would be 10 Tesla. This is bigger than we can make and sustain. And if you spin a strong magnetic field, you get voltage drops, 10 billion volts per centimetre, something cool like that. So if you go to a pulsar, don't take your credit cards. Visiting a pulsar can seriously damage your credit card. And all that rotates as a solid body. We think the pulse period is the rotation period, and we therefore see them rotating, some with a period of 1.4 milliseconds, that's 700 hertz, 700 revs per second. The slowest is about 10 seconds. So in addition to the strong magnetic and electric field, we've got relativistic speeds and strong gravity. Nice problem. We know of about 2,000 pulsars today, seen mainly in the radio, very few in the visible, some in X-rays, and a surprising number in gamma rays. Of the 2,000, about 20 in the visible, 100 X-ray, 100 gamma ray. And of the 2,000, there's a good number in binary star systems, twinned with another star. There's one pulsar-pulsar system, and there's one triple system, pulsar white dwarf orbiting another white dwarf. And there are a few with planets, which can be a bit hard to explain. And probably about 100,000 in the galaxy, and presumably in most other galaxies, but we haven't found any extragalactic ones yet, unless you count the Large Magellanic Cloud, which is like a companion galaxy to ours. Once you've got 10 to the power 27 tons spinning, it keeps spinning. And it's the devil's own job to make it change its spin. So these pulses come round with great accuracy. The period derivatives are between 10 to the minus 12 and 10 to the minus 21. So we've been provided with clocks dotted throughout the galaxy, and we've been able to start testing in new ways Einstein's theory of relativity and theories of gravity and so on. You can measure pulse arrival times to tens of nanoseconds, and if your pulsar is in a binary, you can measure the radius of the binary to 5 microns. That's the kind of accuracy we're getting. Right. This is going to be very fast. What's inside one of these objects? They're also called neutron stars. They're rich in neutrons. They are not exclusively neutrons. There are a couple of hundred, maybe even more than that, models for the insides of a neutron star. And I'm just going to pick out some features to give you a feel for the kind of physics that's going on inside. There is not yet consensus about what's inside. The radius 10 or 11 kilometers, and as we travel in from the surface to the center, the density is going to go up by 10 orders of magnitude. It starts at about 10 to the 7 kilograms per cubic meter at the surface and goes up to 10 to the 18 above nuclear density. One example, for instance, has the surface being a strong iron polymer. You didn't know iron was a polymer. Visual aids are a great help. We have a very strong magnetic field. The iron is not spherically symmetric. It's cylindrical. I'm talking Larmor radii. You can have small, thin ones, cylinders, or big fat cylinders. What happens is you get a fat, a thin, a fat, a thin, a fat, a thin, and you get an iron polymer aligned along the magnetic field line with another polymer next door to it, bound very strongly to it. And so one model allows for this thin iron shell. Conductivity of copper along the field line, conductivity of asbestos across the field lines. Interesting. particularly since these are bodies that are actually slowing. And when it's young and fast, the iron shell will be oblate, and as it slows, it'll want to get more spherical. But it's got a Young's modulus of almost 1,000,000 times that of steel. So how it could change its shape is an interesting question. Going on inside the surface, there's reckoned to be body-centered cubic lattice. Remember, these are neutron-rich, not solely neutrons, so we're dealing with ordinary atoms, probably. But it's quite dense. Okay, undergraduates. Potential well, Schrödinger. Energy levels. 2 electrons per energy level with opposite spin, until you run out of electrons somewhere up here, and you've got an energy level that's empty or half empty. This is called the Fermi energy, or sometimes the chemical potential. It's pretty high. Go a bit further into the neutron star, the density has gone up, the space allowed has gone down, the potential well has got narrower. What happens to the energy levels when you narrow a potential well? Well, it's a bit like squeezing a tube of toothpaste. The energy levels go up. And this first vacant energy level is now somewhere just about as far as I can reach. Okay, so it's up there. Over here is a radioactive nucleus that wants to do beta decay. So a neutron turns into a proton, an electron and an antineutrino. The proton sits tight, it's not going anywhere. But the electron is looking for somewhere to go. It wants to slot into this well. There's a maximum energy that electron can have. And let's say it's about here. So there's the first vacant energy level. This is where the electron, as high as the electron can manage, there ain't space for it. It can't do it. So the decay is forbidden. Beta decay is forbidden. A neutron is no longer allowed to decay. It remains a neutron. So your nuclei end up a bit more neutron-rich. Go in a bit further still, and the energy, the potential well is this width, and the Fermi energy is up there at ceiling level. An electron with that energy has enough energy to cover the mass difference between the neutron and the proton, and it can combine with a proton to make another neutron. So your excess of neutrons is growing. Firstly, because beta decay is prevented, and secondly, because inverse beta decay is allowed. So your nuclei get fat, and they get fatter and fatter the further you go in. And there comes a point where the density of about 10 to the 14 grams per cubic meter, the neutrons start dripping out of the nucleus. The nucleus can't hold on to them all. So you have neutrons roaming around. Now, neutrons are fermions, but if there were a force between two neutrons, BCS theory, they could be considered as one particle with zero spin, a boson. And that will allow, and indeed create, superfluidity. Not superconductivity, unless there's charged particles around, but superfluidity. So help us, we've got this rapidly rotating object with a superfluid material in it. The physics is horrible. You can quantize superfluid. They get quantized into what are called Feynman-Onsager vortices. Millions of little whirlpools in this superfluidity. About 1 million per square centimetre. So parallel to the rotation axis, you have all these little whirlpools, little strands. Magnetic field, of course, is inclined. And some people say the magnetic field might be quantized into fluxions. So you could end up with two kinds of threads in a rapidly rotating body. Yuck, I think is the answer. Not nice. Two kinds of spaghetti crossing each other. And then as you get up towards nuclear density, this area has been quite well researched. The neutrons, the nuclei arrange themselves in various shapes which have been given pasta names. Gnocchi, spaghetti, lasagna, Swiss cheese. This is just outside where you reach nuclear density. Nuclear density, 2 by 10 to the 17. Inside that, we really have no data. So the center of a neutron star is, well, whatever you'd like it to be, theoreticians. You want a quark-gluon plasma? Probably do it. You want a Bose-Einstein condensate? Can probably do it. You want mesons? Probably do it. The one thing I think you can't do is strange quarks, because strange quarks will turn everything else into strange quarks and make a quark star, and that's a bit different. So the physics of these things is fiendish. I am going to pass on to a diagram. This is a diagram of the radius of a possible neutron star and the mass inside that radius, and each of these curves are some of the hundreds of different models. We're now getting a few pulsars with masses around about 2 solar masses, and some of the models won't get there, like these ones won't. They just don't get high enough. So we're getting to the stage where we can rule out some of the models. This particular paper by a very, very able young astronomer called Antoniadis not only has found the first pulsar in a very tight orbit, 2.5 hours, that would fit inside the sun. It's a pulsar with a white dwarf. The pulsar is one of these massive ones. This particular binary system is a very good test bed for gravity. In particular, they've had to worry about scalar fields, gravity scalar fields. We don't usually consider scalar fields, but they've had to. And they've also had to worry about dipolar gravitational wave, gravitational radiation, or scalar tensor theories. So this is a system to watch, and Antoniadis is an astronomer to watch. Thank you for your interest, and apologies for the gallop.
Well, thank you very much. So we have time for some questions. Yes?
Yeah, well, mostly like going off that last slide, and earlier you talked about pulsars might tell us something about Einstein's theories of relativity, and right, like what you were talking about there, like a scalar field of gravity. Can you just elaborate on like what that is and what pulsars might help us answer?
There is a double pulsar binary where both stars are pulsars. And nature has been very kind to us. It's a very, very compact object with a period of about 2.8 hours. So it's really relativistic. And it's almost edge on to us, which is also interesting. And using that system, particularly Michael Kramer in Bonn, has been able to over-determine the system with 5 separate tests of GR out of that system. So they're measuring things like the change in the orbital period, the precession, can't remember what the other ones are, but off the top of my head. But anyway, so they've now got 5 separate tests of GR. And using the data from that pulsar, which they're still observing and still improving, they are able to say that GR is good to probably within about 0.02%, and to make life very difficult for alternative theories of gravity. So they're not ruled out yet, but it's getting sticky. One of the reasons we're pursuing this is that gravity as a force doesn't fit with the other forces we know about. It seems anomalous. And relativity theory doesn't fit with quantum mechanics. So you wonder if at some level we're really understanding gravity, relativity theory, Einstein's relativity theory, is there at some level a problem there, which is why the radio astronomers are really hammering at this. But so far, Einstein stood up to all the tests, but we're keeping going. Well, not ourselves. We're but yes, we're digging.
So there are so many aspects of astronomy that pulsars are pretty quintessential to. I mean, pulsar timing rings for gravitational waves, glitches to help understand the internal structure, things like that. Is there one in particular that most excites you as far as pulsar-related sciences go?
Well, of course, until LIGO scooped them, there was a bit of an unofficial race between the pulsar gravitational array work and the LIGO work, which work in different frequencies, different wavelengths of gravitational radiation, and see different things. But that race is settled well and truly, so that's not happening. I think what amazes me is this subject's now 50 years old. Most things you'd think would have settled into a reasonably mature middle age by now, but this flipping field's behaving like a teenager. It's still erupting, you know. And that, I think, is the most surprising thing. You just don't know what's coming next. You really don't.
Perhaps you could mention about the fast radio bursts. That could be perhaps a next generation.
Yeah, let's see if I can persuade this to go back. Yes, I can. Going back to the Whistler. So, radio astronomers studying pulsars regularly make this kind of plot for the pulsars just to check that it's not local interference. Because local interference won't have this spread. It'll all be, that's local interference. And they were routinely doing this on a particular pulse. This is probably about 8 years ago now. And they found one that was like this, with an enormous spread, implying very great distance. And there was only one pulse. And Duncan Lorimer, who found it, thought, this is curious. And he debated whether to publish or not, and having published, whether to retract the publication and so on. This was actually the first of what we now call fast radio bursts. And pulsar astronomers have now found, where are we, over 20 fast radio bursts? One of which is now known to repeat, but none of the others do so far. And they are a very intriguing puzzle because they come from a lot of electrons away. So you start trying to work out how far away they are. You start, mentally walking yourself through the galaxy. And you notch up maybe 25% of the necessary electrons before you get to the edge of the galaxy. And then the problem is that the electron density outside the galaxy is very, very low. And you have to go zillions of miles to get the rest of the electrons. So we're dealing with something definitely extragalactic, and yet quite strong, and not repeating. And no other electromagnetic counterpart, and interesting puzzle.
Any other questions that might have? Yeah.
You mentioned that when you first saw this repeating pulse, and you went back for months, and it had gone, and you were worrying. Why was it gone?
Right. The quasars twinkle because of the interplanetary medium, the space between the sun and the planets. There are similar effects in interstellar space that cause quite a lot of the changes in the amplitude of pulses from pulse to pulse. And there's one particular kind of scintillation that we now know about called refractive scintillation, where things can go quiet, or I presume loud, for 2 or 3 months. So I was quite lucky it was only 1 month. If it had been 2 or 3 months, I think the project would have got dropped. So it's what we now call refractive scintillation.
Can you elaborate a little bit more about who could have discovered pulsars before you did? There are a number of close calls, right?
I think the main contenders were the X-ray astronomers, who were finding strong signals from objects that I think we knew were binary by then. Did we know Hercules X1 was binary? No, we didn't. Not then. Okay.
Uhuru had to be launched.
Yes, okay. But I think X-ray astronomers were working towards the idea that these objects were binary systems. The snag about trying to detect this from X-ray astronomy is the X-rays depend on the neutron star grabbing material off its companion, accretion. And that accretion is not steady and can sometimes, so to speak, land on the other side of the star, because the period of one of these accreting neutron stars changes quite dramatically. And so it's really quite hard to unravel what's going on. It's all due to the accretion. But we wouldn't have had the cleanness of the radio pulsars. And I think in particular we wouldn't have been able to see the increase in the period due to the rotational model. So I think the main contenders were X-ray astronomers, but are there other opinions? We weren't aware of anybody else doing a similar radio project.
What about optical people looking at Crab pulsar?
You have to look very, very hard at the Crab pulsar, and you have to know the period. So I think probably not.
Okay, one last question. Yeah, with that.
More technical question. I have a more technical question. When you were talking about the precision of the period,
Yeah.
we're quoting relative errors as 10 to the 16, 10 minus 21,
Yeah.
something like this. How you get that numbers with such a slow period? In atomic clock, we have this kind of precision, but with very, very high frequency.
Yeah.
And the high frequency is why we get those so much precision. So I'd like to understand.
Right. That hadn't occurred to me. I mean, you accumulate, you observe, you get the pulse period, you make a prediction that there'll be a pulse at 11:59 tomorrow. You observe at 11:59 tomorrow and you find the pulse is slightly different, so you revise your period, make a prediction, revise your period. It's a cumulative effect.
How long you need to accumulate to get this precision level?
Oh, well, you can project over years. I observe it today. I make a prediction for next week. I observe next week. I make a prediction for a month. I observe in a month. I make a prediction for 6 months. It's not quite as simple as that because you're on a moving Earth, and there's a few things like that. But
I was just surprised by such good numbers.
One of the limitations is knowing the gravitational effect of the other planets accurately enough, and knowing the gravitational effect of the galaxy accurately enough.
Okay, if there are no other questions, let's thank Professor Bell again.
Yeah.